this is work with both my co-advisors, Douglas Eck and Yasho Bengio. So I'm going to talk about new features, multi-timescale features for, in particular, for the task of automatic annotation. So, this talk I will try to describe, first of all, the base model that we presented in Izmir 2001, and we will build on that to build multi-timescale features. Well, first of all, what is automatic annotation? Well, Gert gave a talk this morning that was pretty good describing the automatic annotation, but let me present you a little demo of what it does in real life. So I'm not sure about the volume. So this is the system, the PMC, the system that I will present to you, working in real time over the audio. So it actually looks at 3 seconds of audio to make a decision. And you can look if we average over the whole song. Well, the predictions are pretty good, but instantaneously it makes some mistakes. So sometimes it thinks that Beck is but most of the time it does something pretty good. So let's stop listening to music and be serious for a moment. Okay. So first of all, why do we need the multi-timescale representation? Well, as you know, low-level aspects of music can be easily represented by frame-level features. That's not hard to do, and we use a backup feature representation. But higher levels, such as melody, phrasing, and rhythm, well, you need a longer time scale to analyze those aspects. So what we propose is to combine the different time scales in one feature that we will learn upon. So the idea of multi-timescale is not new. Here are a few well-known, or they're all not well-known, but some pretty old features using multi-timescale. So like there are some that are biologically inspired, like the SAIs and the cortical representation, convolution network and wavelet, which are more mathematically inspired. Or you can just take a set of handcrafted features, like a feature that represents rhythm and then some that represent timbre, and just put that in a big vector, and you will have some kind of multi-timescale representation. But recently, I've noticed that there's a lot of new research on multi-scale representation. These are a few papers from Izmir 2011, and as you have heard today, a lot of talks were about these kinds of representation of audio. So let me introduce to you the model that the model that actually we submitted to MyRex 2001 and to my 2011, and actually, to my surprise, got the best result with a really simple model. So I'll describe what it is. First of all, what kind of features do we use? We call them principal Mel Spectrum components, or PMCs. So we put very little prior knowledge in the features. All we do as prior knowledge is Mel compression, and we have a step of PCA to be able to be adaptive to a given set of audio. So compared to MSVCs, well, here are a few differences. I'm not going into detail about that, but it's just that MFCCs are the most used features right now in MRR, or automatic automatic tagging, and they might not be good for actually as good as we think they are. So how do we compute PMSCs? It's simple, 3-step. We take the spectrum, spectral amplitude, we Mel compress, and we do some PCA whitening. To be precise, the PCA whitening is not data dimensionality reduction. We use the whole PCA space. We just use PCA to rotate our features in a space that's more convenient. So what does this look like? Well, this is a spectrogram. It's pretty dull. It's all blue because all the energy is in the lower frequencies. So it's not log scale. So we apply Mel filters over this. So maybe you might not see it. Here's it's a red line. So the lower frequency, here are the frequency bins and the Mel frequency bins. So the lower frequencies are linear, so they are not transformed. But as we go higher in frequency, the higher frequencies are more compressed. This is just a logarithmic compression. So this is what we obtain if we do the Mel compression. So now our spectrogram is a bit more easy on the eye. We can see the beats and we can see a few of the notes. And by the way, this is the song that I played earlier. It's the Devil's Haircut by Beck. So next step, we want to compute some PCA over this. So we take a few thousand training example and we compute PCA over this, and we obtain this kind of matrix. So these are the eigenvectors of the PCA ordered by eigenvalues. So here the projector doesn't do, it's not really given the real picture that I had. But what we notice is the first few eigenvectors are basically timbre shapes, really almost plane. But as you go low in the lower eigenvalues, you notice that we have this kind of harmonic structure that's captured by the PCA components. And if we apply this matrix to the Mel spectrogram, we obtain a PCA-gram, which is, well, it looks like noise, but there's a lot of information into this. So what do we do with this? We need to, so each column here is what we call a PMSC. It's a principal Mel spectral component. Now we want to do some automatic annotation with that. We need to, well, we want to do some temporal pooling or time aggregation. This is a well-known fact that using statistics over time gives better results for classification for many reasons. The main reasons I would say is stability of the feature and invariance to time shifts and frequency shifts also. So we tried different pooling scale, and we found that going to 2 or 3 seconds is kind of a good plateau for performance. So we're going to go with that. And now, what do we do when we aggregate? Well, typically people take the mean and the variance or the max of the features. We decided to test a few functions. We tested the mean, max, minimum, variance, and we also tried the third and fourth statistical moments. And actually, we were surprised to see that the third and fourth moments really don't do well. So the best performance we got was by mixing mean, variance, maximum, and minimum in the pooling. By the way, I'm going to the performance measure that I use here is the area under the ROC curve, which is basically, if you're not familiar with that, it's a ranking measure. Basically, it gives me the percentage of, if I take 2 random examples in my data set, it's the percentage of chance that they are ordered well in my predictions. So now, if we take our PCA-gram and we aggregate the features, so we take windows of, let's say, 2 or 3 seconds, we obtain something like that after the features are pooled. So this is a window. A column here is a vector, that gives us a good statistical point of view of the features that are into a pooling window. So these are the features that we want to send to our classifier. So here's a scheme of the learning model. Basically, we have our PMCs, and we do the pooling like I just explained. And then the classifier is just a simple, plain, vanilla neural network with one hidden layer, also called a multi-layer perceptron. The output of the classifier is basically the tags that we want to predict. So a few advantages of the MLP is that it scales well to big data sets. It's also good for the multi-label classification task, because you obtain, let's say, 160 different outputs that can give you a measure between 0 and 1 of like how good is the stack on this song. And it can also learn some kind of dependence between the tags thanks to the hidden layer. So we know that tags can have some relation, like rock and pop can come together. So, okay, so I already talked about that. So basically, if we compare the PMSC to other kind of feature, like the basic MFCCs, using the MFCCs but with larger number of bins, adding PCA to MFCCs, just the Mel Spectrum without PCA, we all see that, okay, the PMSCs seem to, they do a better job and they train more rapidly. So now let's extend this model to multi-timescale. Well, we did the thing that we thought was the simplest. So basically, we just take different different frame timescales, and we do the processing in parallel. So the only difference is for different timescale, the Fourier transform will be done with a different number of samples. So the lower timescale, we have, let's say, 1,024 samples, and then for the next timescale we have 2,048, and we go with power of 2, and we augment the timescale, but we keep the same number of mel bins. So basically, the longer timescales get compressed a lot more, but what gets compressed is the higher frequencies, which are already modeled by the lower timescales. So we aggregate. After the PCA and the pooling, we aggregate all these features, concatenate in the big feature vector that we send to our classifier. So this is a visualization of what the Mel spectrogram looks at different timescale. So this is 40 milliseconds, 160 milliseconds, 640, and like if we go to the extreme 3 seconds, well, that's what we get. So. Okay, so what kind of experiments we did? Well, the task is a Thematic Annotation, so we use the Tagatoon dataset, which is the largest dataset that we on the Thematic Annotation that comes with tags and the audio. There's 22,000 songs of 30 seconds and 160 tags. And the model we use is the model I just described. So here are a few numbers, the parameters of the models. So here's a graph of the performance of each timescale individually. So if I take only the features at the 40 millisecond scale, well, we obtain this performance. And when we go up, well, we see that longer timescales seem to perform worse than the smaller ones. But if we aggregate the features together, so this is using only the 40 milliseconds timescale, this is using the 80 and the 40 millisecond timescale, and so on and so on. So we see that using 5 or 6 timescales give us a significant improvement on performance. So we get something over these, having this different representation of audio together. But if you look here, this is the graph I just showed you. Like the performance of higher timescales are really bad, and individually. There's a reason that's easily explainable, is that we, since we aggregate over a fixed window, well, higher timescales have less frames, so the statistics that we aggregate over have, like, they're less stable. So we want to correct that. We did the second simplest thing that we thought about is just that we take this kind of window for a different timescale, and we just we overlap instead of just having consecutive frames. So basically, we get the same number of frames for every timescale. So now, this is the performance of single timescales using this overlap. You see that the best individual timescale is the 90 seconds, 90 milliseconds in this case. And we still see that the longer timescales are worse than the short ones. But if you compare, like here the worst one is at 0.835, and here it's at 0.78. So we're orders of magnitude over the, well, not orders of magnitude, but significantly over better performance for these higher timescales. So it's important to have a lot of frames to aggregate the statistics. So if we aggregate the different timescales together, we see that we still get the same kind of results. Using a lot of timescales improves the performance a lot, and the performance is higher with this than using single timescales, using no overlap. So here the best performance, the mean of the best performance is about at 0.87, and before without overlap it's at 0.87, 868. So we get an improvement. So if we compare to other state-of-the-art models, so this is the multi-timescale that model that I just presented to you. PFC is for full feature classifier. Here is the simple single timescale full feature classifier. This is the multi-timescale learning model that was presented in the paper that is made in the same paper as the PFC. This is kind of a convolution model that adds a layer of learning before the pooling. So it's better than just aggregating the features before learning, but it's longer to train. So you could not submit this algorithm to MyRex due to the time limits. And finally, this other model here is muscles. It's basically it uses SAIs, which are really kind of complex features, and some kind of embedding model that tries to embed in the same space the audio features and the tags. So it's quite surprising that with really basic, simple features, well, relatively simple features, there's no big mathematical transformation, it's all linear, and simple classifier, NLP, we get the state-of-the-art in automatic annotation. I think what we have to take from that is that there's maybe a lot of work to do in feature extraction before going into complex learning for these tasks. We have a lot of improvements. So in conclusion, these are new features that seem to be have some I would say that should be worked on more, but have some potential. In future work, this is like really recent work, and there's still a ton of things that I want to try. One of the first thing that I want to try is to use different pooling scales for different time scales. So instead of having different overlaps for different time scales, just having different aggregation time, that could it would be a wavelet style, I would say. So that could help. Other classifiers could be useful. For example, classifiers that could handle missing features, that could handle doing classification over excerpts of different like at 2 seconds or 5 seconds, 30 seconds, accumulating the data, but you can ignore it if you don't have it. There's another MR task that would be used with those features. Yeah, there's also, I realized that there's a lot of mathematics behind these things that could probably optimize the computation. Lastly, I don't like the acronym. So if you have a good idea of how I should call these features, go ahead. So, thank you.